The ARC-AGI test. Why a thorn for AI? Continuing series in Bergson and holographic theory. Let's take a look. So, in 2019, Francois Chollet introduced ARC-AGI, Abstract Reasoning Corpus for Artificial General Intelligence. He introduced this with a paper in 2019, this one on the measure of intelligence, while at Google Inc. In his interview with Lex Fridman in August 2020, Chollet noted his influence from the great child development theorist, cognitive development, Jean Piaget. Though he noted Piaget's disfavor with current cognitive science and the swing to the core knowledge position of Elizabeth Spelke, and we'll be coming back to this. There is, in the references, is his note about Elizabeth Spelke and Kinsler on core knowledge. There are 400 public tests which AIs can train upon, and 200 private tests, the real tests, which AIs are graded on. Humans can do 100% of the test. Maybe not one single human all the time, as we'll see why, but generally they can do 100%. Chollet thought that 2019 AI could do about 5 to 10% of these at the time. So the AI competition, that is the assault on these tasks, began in 2020 with a $1 million prize, with a goal set at passing 85%, not 100%, 85% of them. In 2020, the winning team got 21%. I'm not sure about 2021 or 2022, and I can't tell if there was competition. In 2023, the winning team got 30%, and 2024, the winning team got 53% on the 200 private test. 61% is claimed on the public test. So as Chollet knew, it is a hard set of tests for AI. But why? So a few of the tests. First one. Take a look at the left. What's filled in? Well, the little yellow square, and it's the only square in the one above that's completely surrounded, a hole, so to speak. Go to the second one from the left. Well, we see two holes, and they're filled in with yellow. Go to the third one. Well, we're seeing a bunch of holes, but they're filled with yellow. Shouldn't be too hard to figure out the fourth one. In other words, to us, these are relatively easy visual, imagination-based manipulations. Take another one. Look at the first one on the left, the input, and then the output. Everything's fallen to the bottom. Second one, input, output, looks like everything's fallen to the bottom. Third one, etc. Not too hard visually. Here's a more difficult one. More taxing. We have to look at it a bit. Now we see that these are all symmetric patterns. So let's look at this one down here. Notice that pretty much looks like the output. And since it's symmetric, if we flip that chunk over and move it over there, well, it's going to fill in the pattern perfectly. And of course, we have to work a little bit laboriously to make sure that all those squares on that output pattern are in the exact position, or we fail. So that could cause a human to flake out on this task, almost purely from a laborious point of view. So AI's assault has been with the full force of its deep learning arsenal, to include chain of thought algorithms, generation of hundreds of solutions in some cases to compare against a target with reinforcement learning. Here's the high scores again. And they were asked to test ChatGPT, I think it's ChatGPT 01's solution, and they did, and they got 21%. And then note that its performance came with a cost. It took 70 hours on a 400 public test compared to only 30 minutes for ChatGPT 4.0. And they note this. You can see similar, does this mean that AGI is here? If we just scale test time compute, not quite. You can see similar exponential scaling curves by looking at any brute force search, which is O x to the power of n. And they say, in fact, we know at least 50% of ARC-AGI can be solved via brute force and zero AI. In other words, you just start generating search trees like all the possible positions in chess until you find the answer. To beat ARC-AGI this way, you need to generate over 100 million solution programs per task. Practicality alone rules this out, this kind of O to the xn search for scaled-up AI systems. Then this is interesting. Moreover, we know this is not how humans beat ARC tasks. Humans do not generate thousands of potential solutions. Instead, we use the perception network in our brains to see a handful of potential solutions. So that's interesting. The perception network. Now, one comment before we continue. I noted a comment string on AI researcher / critic AI Eric Larson's Substack, where the commenter was holding forth that AI can now do anything humans can do, and woe is us, the human race. I noted, not to the commenter, that about the ARC-AGI state of things that wasn't doing all that great on these little tasks. Immediately, the commenter kicked in and began downplaying this, noting that it is, quote, solved, unquote, noting the 61% in the public task. I thought, the strangeness of this position, interesting. On the one hand, AI can do anything. On the other, we know that AI is really, really dumb on things humans can do easily. No problem if you're the commenter, AI will get there via a massive assault, but on this particular set of tasks. They're given a target. They don't really know what general intelligence is, in other words, but you give them an example of it, they're going to go for it, but in that context. Meanwhile, the next Chollet and the next set of tasks is in the wings. So these are very visual tasks. Something about that perception network of ours makes the difference. Cognitive science, thus AI, have no theory of mental imagery. This, to me, is the difference, the very general difference. Not looking at what specific AI people might say with respect to the problems, which it is a problem. In fact, imagery is considered unnecessary for cognition. That's the framework. Zenon Pylyshyn of Fodor and Pylyshyn fame, early in the AI game, Zenon, and the fame is Fodor's notion of modularity of the brain consists of sets of modules, the notion of compositionality, systematicity. We'll see that again. So early in the game, Zenon denied any need of mental imagery. He argued that if images are simply constructed via the data elements and rules for manipulation of the data, the image is simply redundant. All the knowledge is in the rules and data structures in the first place. To quote him, in other words, the image has lost all its picture-like qualities and has become a data structure meeting all the requirements of the form of representation set forth in earlier sections. In fact, it can be put directly into one-to-one correspondence with a set of finite propositions. Similarly, seeing the image, quote-unquote, has been replaced by a set of common elementary and completely mechanical operations, such as testing the identity of two symbols. That's from What the Mind's Eye Tells the Mind's Brain, a famous discussion in cognitive science at the beginning of the dawn of AI. Now, the propositions, due to neural nets, basically, are gone. Well, kind of. But this no need of imagery framework absolutely, totally remains today. Even as we'll see in the current theory of child cognitive development. So what's the core problem this framework is hiding? Well, Cog Sci has no model of perception. Of course, neither does AI. No model of the image of the external world. That is, the image of our external world, that coffee cup out there, is simultaneously our experience, our sentience. If it's not, like I've said, I don't know what it is. This is because their model of the brain and of space and time is entirely wrong. Now, we've noted multiple times, this is Bergson's idea, Bergson's concept entirely different framework, a holographic field the brain is embedded in, indivisibly transforming field, not a series of instances or states. The brain serving as a modulated reconstructive wave specific to a source within the external field, after the holographic analogy up there of a reconstructive wave passing through the hologram. The brain is a reconstructive wave passing through the hologram. Therefore specific to the coffee cup and stirring spoon as an image, and right where it says it is, that image within the external field. And the modulation of the brain is via the invariant structure of the event, the velocity flow fields, adiabatic ratios, inertial tenses, etc., which, by the way, is why Zenon's idea that you can put that event and map it to a set of propositions completely falls apart. Not that this is understood by AI. So you cannot get an image that is experienced from data structures, symbols, network weights, ultimately from transforming bits. You need something, as Bergson argued. It's the point here. AI does not have imagery. That a set of correlated pixels is an image. And by correlated pixels, again, there's the image of a number 9. It's a colored set of pixels of that 28 by 28 matrix. Then becomes a massive set of weights through all the layers. Now, that's what an image is, that set of correlated pixels. But it's only so that number 9 or any other image only via attribution by an external observer. There's no image in the system. It's simply called an image, denoted as an image by an external observer. If one can't see that there's no theory of actual image of our experience, well, I don't know how to help you at that point. So with no model of the origin of the perceptual image, our experience, AI cannot possibly deal with its use in memory, the mental image, or cognition. Better with dynamically transforming an imagery underlying invariance, better way to put it. Dynamically transforming imagery underlying invariance. Psychology knew this before Piaget in the advent of the computer model of the brain. So here's a new ARC test, kind of. Not the greatest ARC test, but take a look at it. We've got some beads. Looks like they're disappearing in a cylinder, and they're coming out. Went in blue, in order, blue, green, red, came out, blue, came out. Looks like red, green, blue. Now there's 2 tunnels. Looks like 2 things happened. Now the order is the same. Now we're looking at it, and 4 things happened. Order comes out different. Oh, order comes out the same. Okay, now there's 3 things happen. Well, how is the order going to come out? I'm sure one can think of a better way to put this into ARC, but then again, everything doesn't have to be transformed exactly into the ARC format with little squares, etc., but this is a start. I consider this a variant of this task of Piaget, with children's age 3 to 7, from the child's conception of movement and speed, where the 3 colored beads, A, B, C, strung on a wire, are moved into a tunnel. Then the tunnel is semi-rotated 180 degrees from 1 to n times. Questions asked. What order will they come out after 1 semi-rotation? Well, they're going to change, right? 1 semi-rotation, they're going to change order. What order will they come out after 2 semi-rotations? That is a full 360 degrees. Well, the order is going to be the same. What order will they come out after any n number of half turns? That is 3 or 5, 6, 7. The child comes to a point in development where he can imagine the consequence of a 180-degree rotation, which moves ABC to CBA, and another 180-degree rotation, which moves things back again to ABC. That is an invariance of order under a 360-degree rotation. We now ask, in which order would the beads come out when the tunnel is semi-rotated 5 or 4 or 6 or 7 to any n number of half-turn question? This is great difficulty. Some children appear to be exhausted after imagining 3 or possibly 4 semi-rotations. That's an important thing to note. Exhausted after imagining 3 or possibly 4 semi-rotations in a row, and they become lost when jumps are made from one number to another. To quote Piaget, but since the child upon each half-turn endeavors to follow the inversion in every detail in his thoughts, he only gradually manages accurately to forecast the result of 3, 4, 5 half-turns. Once this game of visualizing the objects in alternation is set in train, he finally discovers that upon each half-turn, the order changes once more. Only the fact that up to this upper limit, the subject continues to rely on visualizing intuitively, and therefore needs to image one by one the half-turn, is proved because he is lost when a jump is made from one number of half-turns to any other. So the key here, the developing ability to imagine, to visualize, and to perceive invariance over these visual transformations, these imaginative transformations. After this gradual perception of a higher order invariant, the oscillation of order we'll call it, defined over events of semi-rotations, there comes a point when the child can easily answer the ultimate question for the resultant order of any n turns. Piaget's explanation describing the operational character of thought. He says, operations, one might say, are nothing other than articulated intuitions. We'll run across the word intuition. Intuition is another short-term or shorthand for perception, rendered adaptable and completely reversible, since they are emptied of their visual content and survive as pure intention. In other words, operations come into being in their pure state when there is sufficient schematization. Thus, instead of demanding actual representation, each inversion will be conceived as a potential representation, like the outline for an experiment to be performed, but which is not useful to follow to the letter, even in the form of performing it mentally. We're looking at the development of the use of imagery in a logical, compositional, systematic, or, quote, operational, unquote, framework, to use Piaget's term, because you start to see why he ended up using this term, operational. The schematized operations are based in imagery, in our experience. They do not exist without this. You do not get a schematized operation without the experience and the development over time using experience to visualize, to imagine these transformations. This achievement underlies the ease of human performance, I'm going to argue, on the ARC test. Unfortunately, for the information processing, AI, cognitive science framework, this requires a brain in the mode of Bergson's vision, as we noted. The brain is a holographic reconstructive wave passing through a universal field and all that implies, which we've talked about. The Turing machine can't visualize. There is no imagery. So in this series, we've seen examples of this dynamic imagery subserving thought. I've noted them a few times. One I love is Penrose's, a visual proof of a computation that does not stop. That is what he called non-computational thought, which he held requires consciousness, which it does. Or he's, for example, proving that hexagonal numbers, when added successively, always make a cube. And he's folding these hexagonal numbers, like the 19 there, into a three-sided, almost a cube, stacking it over the previous cube, et cetera, et cetera. And one can see this is going to go on infinitely, a computation that does not stop. For all these, remember, these do indeed require consciousness, because you have to have a consciousness integrally participating in the indivisible transformation of the universal field, not a series of states or a series of instants, discrete states or instants. Otherwise, you can't perceive the invariance over the global transformation. The transformation is lost because it falls away each instant, and the next instant is gone, the previous instant is gone. By definition, Turing's definition, this is not realizable via the computational model, a series of states, in discrete states. Can't do this. Others, we noted Wertheimer. Why do angles of a polygon always sum to 360 degrees? And he talks about his intuition of a closed space initially. And then thought about, well, I could break a line. Notice the delta angle there. And then, well, I can break that line all the way around the figure. The line begins transforming, breaking delta after delta. And ultimately, if you remove the figure, you see back to your closed space with all the deltas, a 360-degree closed space. That's from Productive Thinking, 1945. Also from Wertheimer. He noted a cardboard parallelogram task, and the problem was compute the area. And then the 5-year-old girl simply said, well, I can fold it into a cylinder and then give me a scissors and I can cut it to make a rectangle and then I can compute the area. This dynamic transformative thought of imagery. Even in the context of the mousetraps, transforming mousetrap 1 to mousetrap 2, a common sense of knowledge problem. Just looking at all the visual transformations that have to be done to move mousetrap 1 there to mousetrap 2, bending the arm, bending the other arm. So shorten one arm, etc. Introduce the platform, staples, etc. All kinds of visual transformations. But these are multimodal analog transformations. This is an important paper in Influence Me by Aaron Sloman. The role of intuition and non-logical reasoning in intelligence. Note there the concept of analogical representation, applying to problems of a simulation of perception, problem solving. That little figure there was one of his, figure 3, the pulleys. If you look at it, you can see what's going to happen. You can imagine it. We'll just animate it for a second. The weight comes down, and the other board comes up. Notice things that you see in the animation, that actually the little rope on the boards actually pulls out a little bit. Either that, or you'd have to compensate. The board would have to grow longer so that the little rope there would stay on the looking at the right side, would stay vertical. So here's the problem: reduced to a correlated static set of pixel group after pixel group after pixel group, which one would have to do to represent that transformation, a series of such, a massive amount of information is going to be lost. AI does not have the needed representational power, the power that's implied in analog visual transformations over which invariance is perceived. Sloman clearly understood AI's representational power problem, but never its implications for the brain, that is, for the type of device required, namely a device like Bergson's that actually can account for how we perceive an image in the first place. That's where it starts. I know he never could get there because I tried an interaction with him one time, and he was not interested. Pretty much stuck in his AI vision. We noted Chollet's influence from Piaget, the core knowledge question. We can assume this influence, his actual knowledge of Piaget, is probably fairly small, and his acceptance of Cog Sci's, cognitive sciences, the devaluation of Piaget, and the core knowledge, his acceptance of the core knowledge concept for development, that is a form of innate knowledge, not developed. Again, here is ARC's assumed core innate knowledge priors. We noted objectness. That's a given. Goal directedness, a given. Numbers and counting, an innate given. Basic geometry and topology, an innate given. Much of this comes from Elizabeth Spelke, and this is the 30-year plus effort of research and assessing Piaget. Well, I'm going to say initial assessments of Piaget, and then marching on from that. In my opinion, from the framework of information processing. It is, most of this started in the 70s. I see papers from Spelke in 1985 already, with where the information processing framework, the computer metaphor of mind, had swept into cognitive psychology and was embraced. And Piaget was looked at through this lens without any interest in what Piaget might imply outside of that lens, that framework of the computer model of mind. So in Spelke, you'll see definite shades of Fodor and Paulition, modularity, compositionality. So we'll just look at number here for a bit, because that implies we're going to see a whole lot of things that AI would be giving itself that can't be, that there's a developmental sequence, and it's profound. You can't just jump in at some point in the developmental trajectory and start there and think you're going to have the same thing, the same capacities of a brain. If the brain has got to go through this developmental trajectory for some reason, you should be looking at it. So we'll look at number, like I said, now innate, but well, only somewhat. And far from so from Piaget, with significant impact for the problem of imagery and representation, as I've been saying. So that statement, numbers and counting, objects can be counted or sorted by their shape, appearance, or movement using basic mathematics like addition, subtraction, and comparison. That's it. That, he'd say, is a given for AI. I'm stressing this again because this actually comes right back to the problem. What's the real problem with the ARC-AGI test? I think the above is an overstatement by ARC, probably just to keep things short. It hides very much complexity. Spelke, here's an article, 2017, Core Knowledge, Language and Number. To quote, natural number concepts arise through the productive combination of representations from a set of innate, ancient, and developmentally invariant cognitive systems of core knowledge. In particular, natural number concepts depend on a system for representing sets and their approximate numerical magnitudes. Hereafter, the approximate number system, ANS, got to remember that. So that's sort of an innate system, approximate number system, and a set of systems that collectively serve to represent objects as members of kinds. So the ANS, the approximate number system. Some of the evidence for this. Infants and animals can respond to cardinality of a set with ratio-limited precision. For example, infants can distinguish 18 from 6 in an array, but not 8 from 4. So they can see the top array and see there's a difference there, but the bottom array, the purple array, not. Now, these are very young infants. So the 8 from 4 has got a smaller ratio, 2 to 1. Infants add and subtract from successive arrays for a rough estimate of the difference. And Spelke details a ton of such findings, but clearly does not hold that the ANS is equivalent to the concept of number, as ARC is implying. Objects as members of kinds, she notes over there in the paragraph on the left. Well, just to be very brief, one can see intuitively that there's going to be some developmental interplay here. 7 cats might not be seen the same as 7 things, where you've got 4 trucks and 3 tomatoes. You might see these are different categories and something's going on different for the child. So this latter, the things being a higher order, later concept. She goes on, none of these core systems is unique to humans, but their productive combination depends on the acquisition and use of natural language. And that's going to be her fundamental thesis, that it's language that makes all the difference ultimately. And this may be correct at some level, to some degree. But what it means for the nature of the brain is likely very dependent on your framework. Note the language of and the use of representations and combining representations. Just a rough idea. We're sort of back to Fodor's modularity, the flavor thereof. You have a system representing colors, a modular system, brown, red, blue, and another system, modular, representing animals, cow, horse, frog. Now you combine things from these systems, that's the systematicity, and you get a brown cow or a blue frog. So that's kind of the mindset of what we're combining representations, quote unquote, from various systems. But again, remember, these too require representations. Just what are these representations? Well, we were saying they're basically imagery, but that's not what Spelke is thinking. So on reading this again, after 50 years, Piaget and the child's conception of number, what you see is one huge discussion of the development of flexible, that is operational, that word again, imagination. This book, as far as child development, would precede the children's, basically it's contemporaneous with the child development of the child doing in his movement and speed concepts. Don't forget, you've got tons of Piaget books. Conception of number, the conception of space, the conception of movement and speed, the conception of time. So there's 243 pages of experiments on number here. Experiments and discussion. This framework, the operational or logical employment of images, has been stripped away in the subsequent 50 years of the information processing-based analysis of development. Well, as I noticed, kind of stripped away at the very beginning of the analysis. For this particular framework, has no place for imagery, as I noted, via Mr. Zenon Palishin, expressing that framework. So one example in Piaget, children roughly 4 to 6 or so. So 10 vases, they're showing 10 vases. I'm only showing 6 here to make it simpler for me. What should we put in them, we asked the children. Let's get some flowers. So they get some flowers, and they bring in a bunch of flowers, more than there are vases. And then the child either makes a row the length of the vases, as such, or places the flower by each vase, as such. Now, he's asked then, check your work. Now, he puts a flower on each vase, as such. So, no, that's not going to work for the child that just put a big row this length of the vases. He's going to have some left over. So things aren't going to work. But let's say, in this case, the child had the one-to-one correspondence, so to speak. So the flowers are now taken out and bunched up. Or the vases can be bunched up and the flowers left in a row. We'll see. And he's asked, is there still the same number of both flowers and vases? Again, I said you could do the opposite. I noted, bunch the vases, leave the flowers there. Ask the same question. So Piaget notes 3 stages. Stage 1, global comparison, without one-to-one correspondence or lasting equivalence. Children who simply made the flowers the same length as the row of vases, for example. Here's Gui, 4 years, 4 months. He thought, well, they're the same. So he's asked, can you put the flowers in the vases? He did, but 3 are left over. The flowers are now taken out, bunched. Is there the same number of vases as flowers? No, he says, there are more vases. If we put the flowers back in the vases, the experimenters ask, will there be 1 flower in each vase? He says, yes. Why? There are enough. The vases are closed up, the flowers spaced out, and now there are more flowers. So he simply cannot keep an equivalence, not a lasting equivalence or a one-to-one correspondence. Stage 2, the intuitive. There's a one-to-one correspondence without lasting equivalence. These children make the one-to-one correspondence, but also cannot deduce the lasting equivalence of sets irrespective of the arrangement. The one-to-one correspondence is not yet operational. So Dai, 4 years, 6 months, he constructs the one-to-one correspondence. The flowers were taken out, bunched together. He's asked, is there the same number of flowers in vases? He says no. They ask why. There are more vases. Now the situation's reversed. We bunch the vases. Now he says there are more flowers. So again, can't hold the equivalence. Stage 3, operational. A one-to-one correspondence with lasting equivalence. The operation is no longer affected by intuition, that is just raw perception. He can get past the raw perception. He can manipulate it. The children grasp both reversibility and equivalence. Example, FET, 5 years, 5 months. The flowers are taken out of the vases and bunched together. He's asked, is there still the same number of both? Yes. And if we put them like that, as such, yes. Why? Because they were inside the vases, he says. So that little statement, because they were inside the vases, holds a quite an achievement of operations here just to make that statement and understand what it means. For Piaget, the operations imply the progressive reversibility of the course of the imagery of perception. The child has discovered that any spatial modification of the elements can be corrected with an inverse operation, what he calls reversibility. And this is understood as the source of equivalence. It guarantees the necessary and lasting equivalence of sets. So the one-to-one equinumerosity, as it's called today, principle is part of the number story. Another is cardinality. An example of the problem in a memory experiment. He discusses this in Child's Conception of Number, but this is from a slightly different book, but the same thing. Children 3 to 6 are shown the top row there, seriated row of sticks, A. A week later, they're asked to reproduce what they saw. They're asked to remember what they saw. And a week later, asked to reproduce what they saw. And then 6 months later, they're asked the same thing. So at around 3 to 4, the series is reproduced as in B. No seriation hardly whatsoever. And then slightly older children, 4 to 5, remember the form of C, a bit of seriation. And a slightly more advanced reproduction is D. You can see still not really seriated. And at 6 to 7, the child remembers the original series, A. That is, he can now reconstruct the series A. Why is this interesting? Well, again, you've got concrete operations forming. To order a simple series, ABC, that sticks there, where A is longer than B and B is longer than C, one must simultaneously relate or coordinate the height of B relative to A and the height of B relative to C. That is, B is both simultaneously taller than C, but less than A, shorter than A. So you have this basic compensation and reversibility of thought going on relative to that perception. To Piaget, this is fundamentally based on the intercoordination of action. Well, in this case, a mental action, though it could be based equally on doing the physical action and being transduced to the mental action. Here's another case. This is from the child's conception of time, children 5 to 7. So there's shown this flask, the top flask, and it's emptied in a series of stages via a little valve as such. So it gradually empties out completely, and this flash number 2 there fills up. The children are asked to draw each stage on a separate sheet. So they draw each stage, separate sheets, so they have 6 sheets. The drawings are shuffled. The child is asked to order them. And then the drawings are cut in half. Again, asked to order them. The stages. Well, complete failure on the uncut drawings. For example, that might be what your uncut drawings look like. You can see the flow is lost between the beakers. Then there's ultimately success. They can order the uncut drawings, but complete failure on the uncut, even with coaching. It might look something like that. Even with coaching, they can't get them in the right order. So, per Piaget, regardless of the irreversible flow of the water, they must perform a reversible operation. They must construct a series, A greater than B greater than C, where the arrows carry a dual or simultaneous meaning, standing for precedes as well as follows. Again, focus on B. So B precedes A but follows A but precedes C. So it's a pure problem of representation, says Piaget. Yeah. Now you have to think what that means. A problem of representation. It means you're dealing with the need for a simultaneity of relations. Again, fixing on B preceding C but following A simultaneously. So that's the problem of representation, actually in an indivisible time, a flow of time, as I said. So Piaget, discussing the simultaneity in the context of seriation, cardinality and number, termed this a psychological simultaneity. And one could ask, well, what is a psychological simultaneity to an AI, which is by definition a series of discrete states? How do you get simultaneous states in an AI? This achievement can collapse in aphasias. This is interesting because the neurodynamics underlying this can be destroyed with a brain lesion. Cassirer noted this. He says, this is in the Philosophy of Symbolic Forms, 1929. The pathologies indicate that the contents of certain sensory spheres seem somehow to lose the power of functioning as pure means of representation. Again, we're talking sensory spheres, visual, auditory, that is, failures of imagination. He noted one patient given a set of things to count could not progress in order, but frequently went back again. If he had arrived, for example, at 6, he had no comprehension that he had a designation for the quantity thus far achieved, that is a cardinal number. When asked which of two numbers are larger, say 12 or 25, many aphasists can only do so by counting through the whole series, determining that in this process the word 25 came after the word 12. Now I know Spelke noted this particular aphasic problem, but does not interpret it in the same way at all, as we're about to see. What Cassirer says is where quantity no longer stands before us as a sharply articulated multiplicity, it cannot be strictly apprehended as a unity, as a whole built up of parts. Again, every number must carry a dual role. This was Cassirer's explanation of things. Notice if you want the sum plus 7 plus 5 or the difference 7 minus 5, the decisive factor is that the number 7, while retaining its position in the first series of 7, now is taken in a new meaning, becoming the starting point of a new series where it assumes the role of 0. We're also showing not only 7 plus 3, but 6 plus 3, 5 plus 3, etc. Again, he says, the fundamental unities must be kept fixated, but precisely in this fixation be kept mobile, so that it remains possible to change from one to the other. Again, we're not talking anything AI-like here. The number 7 must maintain its meaning as 7, yet simultaneously assume the meaning of 0. He says, it is this articulation of one and the same element of experience with different, equally possible relations in simultaneous orientation in and by these relations that is a basic operation essential to thinking in analogies, as well as intelligent operation with numbers. And I discussed this in a discussion of analogy. I can't do justice to the richness and depth of Piaget's analysis of this operationalizing of the imagery of perception. A bit more of the flavor. Again, quoting from the Conception of Number book. The problem in chapter 1, in other words, earlier in the book, was deciding whether a quantity A1 equivalent to A2 remains equivalent when subdivided or poured into a different container. This So 1 second. So this is the classic conservation task of Piaget. We have two glasses, A1 and A2, both at exactly the same amount of liquid. We take A2 and we pour it into B1 and B2. And then we ask the question, is the amount in B1 and B2 still the same as A1? This is going to apply to number as well, because we have to conserve the elements of the number when we move those vases and flowers around. And of course, there's going to be a standard phenomenon in the Piagetian world of stages, where initially the child cannot do this. And only after he learns to do compensation mechanisms in thought to adjust the height and the width of the glass conceptually, to allow for the fact that you've got the same amount of liquid, the same volume. So, to go on with the quote, the solution requires the capacity to unite parts into a whole, to divide a whole into parts, to coordinate equivalences, and to multiply relationships, all the additive and multiplicative compositions. So one can see why this is a dense reading. I went through virtually all these books 50 years ago, and it's dense. It takes great concentration, because he's explaining this in this detailed way, analytical way throughout the book. And you can see why people in this realm haven't necessarily read Piaget at all, or much of it. So he says conservation is at the same time the result of composition and the invariant. It is a perceptual invariant, a conceptual now, that makes composition possible. Then he says, the third stage becomes possible with the constitution of two interdependent systems, the grouping of multiplications of relations and the group of numerical multiplications, both of which coordinate into a closed and reversible whole, the operations involved. So the operations form a closed, reversible whole. He's talking about a mathematical group here. And the properties, the four properties of its operations, namely closed, associative, and inverse operation, and identity operation. In the concrete case of the rotations of a square there around its center, the identity operation is a 360-degree rotation, which leaves everything unchanged. Each operation has an inverse, 90 degrees and minus 90 degrees. The operations are associative. 90 degrees plus 180 is a 270-degree rotation, another element in the group. And all these rotations are within the group. It's closed. Mathematical group. Now, Cassirer first published this in French in 1938. We see it here in 1944, the concept of group in the theory of perception. Whether Piaget got this from Cassirer or not, I don't know. I see a 1938 publication of Piaget where he's talking about this already. He definitely exploited it to a great degree. Cassirer says there, the first attempt to apply mathematical speculations concerning the concept of group to psychological perceptions of problems of perception was made by Helmholtz. So one wonders how this was so easily dropped. In the rush to the computer metaphor of mind, all this was disappeared by cognitive developmental science. And one wonders, was this really that wise? So cardinality, equinumerosity, which is to say one-to-one correspondence, certainly remains seen as underlying number. It's far from simply innate. Here's an article from Cognitive Science 2013, Sarnica, Wright, and we see that they're saying that what's required in a number is the cardinal or cardinality principle and exact equality or equinumerosity. And here we're noting, for example, that they say, going on with the article, what does it mean to understand number? Talking about Piaget, the key number concept is equinumerosity, sometimes called exact equality, the idea that two sets have the same number of items. Then they note a different operational number definition of number knowledge, realizing the cardinality principle of counting. So one wonders, there's an entire chapter on the operational development of cardinality and ordinality, along with another chapter is the equinumerosity, one-to-one correspondence development, as part of number in this book alone, as part of a consistent theoretical structure. And what we see is Sarnica coming to the conclusion that indeed the cardinality principle and the equinumerosity principle are both necessary to understand number. So one wonders, well, how did they ever get dissociated in the first place? Except that somehow Piaget was completely thrown away. Interesting. So it would take a study of a now very huge literature on number to determine what exactly has been undone in Piaget, if anything, truly. Sarnica and Wright, to me, are awfully close to Piaget, with everything and more said in this video just kind of stripped out. They do note a difficulty here with explaining their findings via some concept of mapping to Spelke's ANS. So they take issue with things there. But in general, somewhere along the line, much of Piaget was thrown away. Some of it was because, well, we see things like the little conservation task I noted. Well, they would see things like the child being able to do it earlier, or would be able to do it under different circumstances, different arrangements, different instructions, or children could do things later. There was a whole slew of these things. But again, what actually was done to Piaget's theory, or undone, would be an extremely interesting exercise and vast. So Piaget's emphasis on the operationalization of imagery, Cassirer's sensory spheres, has been stripped out, as noted. Spelke uses Fodor's concept of modularity, distinct modules, communicating, combining concepts to make new ones. How that would work, one wonders, how it would account for things like coordinating the two different velocity flows in the beakers, for example, or understanding the odd-even rule as invariance under half-turns tunnel rotations, and a slew of other things in Piaget would be quite interesting. Piaget is a vast description of the development of human general intelligence. In my opinion, there's a pile of ARC tests that are implicit within it, maybe not looking like ARC test right now, but with some creativity. I think that would be a very interesting exercise. But it requires the brain to be a device, quote unquote, after Bergson and Gibson's model. So I would say any development of ARC tests from Piaget would be quite a challenge for AI ultimately. Postscript. A query I saw discussed to ChatGPT recently. Me asking ChatGPT just now, Alice has 3 brothers, and she also has 4 sisters. How many sisters does Alice's brother have? Before the answer, let's do the human thing. Now knowing at least some of the complexity beneath it, if we do compositional or operational imagery. So we have Alice, and Alice has 3 brothers, and Alice has 4 sisters. And we got to remember Alice is one of the sisters. Move her up there. And then we see that, well, each brother has to have 5 sisters. Looks fairly clear. So ChatGPT says, Alice has 3 brothers, and each of Alice's brothers shares the same things, siblings, including Alice herself. since Alice has 4 sisters, each of her brothers has 4 sisters, including Alice. Therefore, the answer is Alice's brother has 4 sisters. Me, you are wrong. Might you check your answer? ChatGPT, you are right. I made an error in my explanation. Let's go through the problem carefully again. Final answer, Alice's brother has 3 sisters. Okay. Just wondering, how much is current cognitive science really helping AI? So next, we'll see. Till then, again, a lot of these thoughts in this book. Till then, signing off.